Hello gentlemen, this is the second part of the polynomial video. Hopefully you got the introduction, you understand the leading coefficient test, and you understand continuity. Now what we're going to do is we're going to talk about some more properties of polynomials and graphing, and specifically we're going to look at zeros, and then we're going to do a bunch of examples. So let's talk about the zeros of a polynomial function. We've already talked about zeros a little bit last week, but in general, a zero of polynomial is a situation where the function, if I plug in that value x, then it will produce a value of 0 in the function. In other words, if x, let me get my pen here, if you know, a is a 0, then f of a is equal to 0, and the x-intercepts, and we'll see it on the next page, is going to be a 0. Okay, so we're going to talk about zeros a little bit more. A function has at most n real zeros. So if I have a polynomial of degree 4, there is at most 4 real zeros. Okay, very important to understand. Then we also have at most, and not necessarily going to have them, but at most we're going to have n minus 1 turning points. So if we have a situation where we have a polynomial of degree 4, then I can have at most 4 zeros and at most 3 turning points. Okay, and that's important to understand as we start to talk about graphing. Turning points are relative max and min points. In other words, if I give you just a little graph here, okay, if I give you something of degree 4, okay, there's something potentially of degree 4, because I could have 1, 2, 3, 4 zeros, and I would have 1, 2, 3 turning points. And these are the turning points. These are the relative max and mins, or turning points, where I'm going from decreasing to increasing, or increasing to decreasing. Those are turning points. Turning points are when I change from increasing to decreasing, or vice versa, decreasing to increasing. Okay? Here's a statement about zeros. If x equals a is a zero of a function, then x equals a is a solution to f of x is equal to 0. In other words, you know, I would have here, you know, f of a was equal to 0. It's a solution to this. These are all equivalent statements. X minus a is a factor, and a comma 0 is an intercept. Make sure you guys understand this. This stuff is important. You should know it. This should be somewhat familiar to you. And we're going to use this in a couple of our examples. A couple things about repeated zeros. It's going to help us with our graphing. We have a couple different situations. If k is odd, so if I have this factor, so say I had something like f of x equals x cubed x minus 1 squared. We'll use that example here. Here I'm going to have 2 zeros. You should see that x is equal to 0. It's going to be a 0, and x is equal to 1. Those are both zeros of this function. Okay, but they're multiple zeros. This is a double root. X equals 1 is a double root. X equals 0 is a triple root. And so what does that mean in terms of our graph? Well, if k is odd, like in the situation with the x equals 0, the graph will cross the x-axis at that point. Okay, so we're going to cross at x equals 0. If we're even, the graph will touch at x equals a, but does not cross. So we're going to touch the graph, we're going to touch the x-axis at x equals 1, but we're not going to cross it. And when I mean touching, it's something like this. At x equals 1, I would come down, touch, and then come back up. Okay, something like that. Where I cross, if I was going to cross, it's going to actually cross like that. Okay? Let's do an example. I want to graph this function here. And so I want to first look at the leading coefficient test. Okay, I have a degree of 4, and I have a positive leading coefficient. Here, the leading coefficient here is equal to 1. Let's make a note of that. Is 1 here. And I know, because I'm an even function, that with a positive leading coefficient, that I'm going to go off to infinity as x goes to both positive infinity and as x goes to negative infinity. Okay, the graph rises to the left and to the right in both situations. Let's talk about the zeros. The easiest way to find the zeros here, I would first factor this. I will get here. Okay, hopefully you guys can see that. So I have 3 zeros. I have x equals 0, and that's when this term right here is equal to 0. And it is a multiplicity 2. And again, let's go back to what we just learned about zeros. That means that the graph is just going to touch at x equals 0, but not cross the axis. Graph touches, but does not cross at x equals 0. I have 2 other zeros here, x equals 5 and x equals negative 4. That's when these two guys are equal to 0. They're both of multiplicity 1, and because they're of multiplicity 1, they're going to actually cross the x-axis. Okay? So if I look at that here, this is what I'm going to do. Again, I'm starting, I know my end behavior here, I know it here by my leading coefficient test. I determine my zeros and what those zeros are going to do. And so I have here x equals 0. I'm just touching right there. Okay? Here I'm going to cross, here I'm going to cross. I have here 3 turning points. One is right there, one is right there, and one is right there. Okay, and I can find those using my calculators: relative min, relative max, relative min. Functions going from down here, we're going to go from decreasing to increasing. Then I'm going to go from increasing to decreasing, and then decreasing to increasing. So I'm going to have those 3 situations there. Okay, so hopefully you guys can do that. First thing I would check is end behavior, plot your zeros, and then use your zero rules with the multiplicity to decide if I'm going to touch or cross the x-axis. Here's another one. Actually pretty easy one because I've already factored it for you. But we should note that this is going to be a polynomial of degree 5. Okay, because I have x squared, and an x. Positive leading coefficient, which again is going to be 1. And that tells me now I'm going to have a little different situation. As x goes to infinity, f of x goes to positive infinity. As x goes to negative infinity, f of x goes to negative infinity. Okay, because my leading coefficient here is x to the 5th. Remember, whenever I have an odd power, odd degree, I'm going to go a negative number to an odd power is still negative. That's why I'm going to go down to negative infinity over here. Okay? What does that mean? The graph's going to rise to the right and falls to the left. In other words, if I have something like that, it's going to finish like that and then coming down like that. Okay? Now, the question is what happens in between here? And that's what I'm going to use my zeros to tell me. Let's look at the zeros that we have. Again, you should see 0 is obviously a 0 of multiplicity 1. Because of multiplicity 1, it means I'm going to cross the x-axis at that point. I should also see that negative 3, this part right there, is going to produce a double 0, or multiplicity 2, which means I'm just going to touch, but I'm not going to cross at x equals negative 3. I should also see that x is equal to 4 is a 0 of multiplicity 2. It's a double root. And again, that means I'm going to touch the graph, but I'm not going to cross the axis. All right? So if I look at this, again, I'm going to look at my end behavior first. Whoops, I'm sorry, let me go back there. I'm going to look at my end behavior over here. I'm going to graph my zeros. I know I'm just going to touch right there. I know I'm going to cross right there. And I know I'm going to touch right there. So I have to fill in the dots. So if I come in here, I know I'm just going to touch. Then I'm going to come up here. I'm going to go through x equals 0. Then I'm going to touch again here. All right, so make sure you understand that. Here I have 1, 2, 3, 4 turning points. Okay, at max I can have is 4. And these are my relative max, relative max, relative min, and I can use my calculator to find those. All right. Now let's do a word problem. Open box is made from a square piece of material, 36 inches on side. By cutting equal squares with sides of length x from the corners, we want to maximize the volume here. So I'm going to cut out an x on each side. If I'm going to maximize volume, I need to come up with a volume equation. Okay, volume is going to be base times width times height. Height is x. and because I'm cutting the same amount and I'm starting with a square piece, this side right here and this side here are both the same, and it's 36 minus 2x. Our domain here, important, x is going to be equal to between 0. Obviously, if I don't cut anything, it doesn't make sense. But if I go bigger than x is equal to 18, then I don't have enough material. So my domain for this particular problem is going to be between 0 and 18. Okay? And so we want to graph this function, and then we'll be able to use our calculator to find where the maximum value is going to happen and what that maximum volume is going to be. All right? And so to do that, let's look at what we just learned. This is going to be a polynomial of degree 3, and I'm going to have a positive coefficient, because when I square this term here, I'm going to get 4x squared times an x, and so my leading positive coefficient here is going to be 4, okay? And that means that I'm going to go off to positive infinity and negative infinity when positive infinity when x goes to positive infinity, and negative infinity when x goes to negative infinity, okay? Let's talk about the zeros here. The zeros are going to be, obviously x is equal to 0, and it's going to be a multiplicity 1, means I'll cross at that point. And the other 0 is going to be x is equal to 18 of multiplicity 2, which means I'm just going to touch the graph at that point. Again, so if I graph this, if I look at this, again, I'm only interested on 0 to 18. If I was to continue this graph would come down that way, go off to negative infinity. This is going to just touch, and then it's going to go up like that. But I'm only interested in this part of the graph, because that's the only area my solutions can be. If I want to find, what am I looking to do? I'm looking to maximize the volume. Here's the volume, here's my max point up here, somewhere up there. I know how to find that because I can use my calculator to determine that. If I do that, I'm going to find that x is equal to 6 inches will give me the best answer, it'll give me the maximum volume. Okay. To find out what the maximum volume is, I then plug that back into this equation right there. If I do that, I'm going to find that the maximum volume of the box is going to be 3456 cubic inches. Again, make sure you put your units where appropriate. Here's some practice problems, fellas. I want you to look at examples 4, 5, and 6 in section 2.2. Here are some practice problems. They shouldn't be too bad for you. Again, if you have any questions, you need to email me. Really what we looked at doing today is continuing looking at polynomial functions. We talked about the zeros, and if zeros had different multiplicity, what it meant in the graph. Okay, and then we applied those to a couple example problems. Okay, fellas, have a good day.